This lesson is over section 8.3. I'm going to do the lesson in two parts. It's going to be two separate videos. We'll do 8.3A. We'll do problems 1 through 16 odd, 19 through 41 odd. And then after we finish this, I will send you another one. It'll be 8.3B. On 8.3B, we'll pick up where we left off here. We're talking about vectors. The nice thing about this for you two guys over at Fruitvale, we've covered vectors pretty well in comp math and also the other times that we've been together working on math. The UIL math, the TMSCA math that we go over, we've pretty well covered vectors. We'll do a few new topics on here. The problems will not be as difficult as the problems we worked at Larry White wrote or some of the other people for UIL math, but we will go through a few facets that maybe we haven't gone through. Now let me give you a little slight review. A vector has two things. It has magnitude and direction. Vectors are drawn like this. The length from the tail to the head is the length, and it has this direction. If I come over here and draw a vector that has the same length and in the same direction, it'd be hard for me to do. But if I did that, then we would consider these two vectors to be equal if they have the same length and in the same direction. So a vector has magnitude and direction. Keep that in mind as we go through the information that's on this section. Look at problem 1, and I may be off here, off camera a little bit on here, but if I look at problem 1, it says name all pairs of vectors that appear to be equal. Now I'm on page 755 right now, so if you would look on there, if I just look at that, it looks to me like M and P have the same direction, same magnitude. So these vectors are considered to be equal. Also, if I were to look at N and R, those two vectors look to have the same magnitude, in other words, the same length, and they have the same direction. So we would consider those vectors to be equal. If I look at 3, it says name all pairs of vectors where the first is a scalar multiple of the other, with the scalar being positive. So, for example, if I were to look at M and at P, we could say that P is 1 times M. Or I could say, if I look at T and M, for example, I could say, okay, if I multiply T by 2, I would probably have M. So a scalar is just multiplying the length of a vector by a number, which is called a scalar. Now, if I look on down, starting at number 5, and like the first one says, negative B, and they've got B drawn something like this. Well, negative B means that we just turn it around and draw it in the opposite direction. So if this is B, then this would be negative B. The direction is exactly the opposite, so it's negative B. The length is the same, scalar is the same. They have where we add two vectors. Look on down at number 9. I see that A looks something like this, and we're going to add B to it, and I see that B looks something like this. And so if I'm going to add those vectors together, now there's 2 ways that they do it. Actually, both ways are the same. They just go by different names. If I'm adding these together, then what I want to do is connect tail to head. So I'm going to take, here's A, and here's B, and the resultant vector of A plus B is this right here. Now, that's one way of doing it. They go through a process, and it gets you to the same place, and they call it kind of a parallelogram type thing. They would take A like this, and they would take B like this, And then they're going to draw a line that goes kind of down through the middle of it for A plus B. And basically all they've done is taken this vector and placed it here. Or at the same way, they could have said, well, they take this vector and place it here. We end up at the same place if we do it this way. I like this way. To each his own. Both ways of thinking of it gets you at the same place. I want you now to turn over to the next page. We will omit 17 and 18. The problems do not stand alone, so we will not do it. And I want you to go to number 19. Can't get the lid off that thing. Okay, on 19, they have two vectors drawn on the XY coordinate system. This one ends, the point at the end would be, looks like to me about a 4/8. And the other one here looks like that it goes about to a -8/8. Now, a way of measuring, or a way of representing vectors on the XY coordinate system is the same thing. The component vector, component vectors of this is the x equal 4 and the y equal 8. And this is the same as the point right here, 4/8. This is the same as the point at the end of the vector, 4/8, when it initially started at the origin, or 0, 0. And so what they want me to do is add these two vectors together. In other words, one way I could do it is take this vector and move it here, like so. And what I get right here would be the resultant vector. My drawing is not to scale, but you understand what I'm saying. Now, to find the end of this thing, we would add the x's and y's together. Sure enough, should have this thing further over when I do this. But when I do it, if I add my x's together, I got -8, +4. So -4 would be the sum of the x component vectors. And 8 and 8 would be 16, and that would be the y value, or the 16 for the y component vector. And this, -4, 16, is the sum of these two vectors. Graphically, did a terrible job drawing it, but graphically you understand I would go and I'd put this up here and go tail to head and tail to head, and at the end of this, when I draw it up here, would be my resultant vector. Okay, let's see what else we need to cover. I think that'll pretty well get you through problems 19 through 24. I want you to look at problem number 26. And we've seen this before. We ran across this in our UIL math. But we want to add these vectors together. Now, this vector right here could also be written in this form. They just give different forms of it. This would be -1 and a +2 for this is my x component, which is -1, and my y component vector is a +2. Over here, I've got 1 for the coefficient I, so my x component is 1, and my y component is a -1, the coefficient of j. If I add these together, I'd add them exactly the way I did the one that was up here a while ago. If I had it in this form, -1 and 1 is 0, 2 and -1 is 1, and so here's my resultant vector. I can write it in this form. This is one way of writing. I can also write it in this form. If I add my i's together, I do not have any i's. That would be like 0i. If I add my j's together, 2j and 1j is j. So I have 0i plus j, and this is the sum of my vectors. If I do it like This, if I write it in that form, this would be my answer. If I do it in IJ form, this would be my answer. Both of these mean the same thing. 0I, 1J. X component 0, Y component 1. Meaning exactly the same thing. For example, if I looked, I think I saw it a while ago, if I do 27, instead of writing it in the IJ form, they wrote it in this form here. But the concept is the same, and we do it both ways. Okay, let's look down to number 29. Making sure I had that thing running. The other day I started one of these classes and I clicked the wrong thing to start it. Okay, look at 29. Okay, now it asked me on these, if I read my directions there, it says that for each pair of vectors u and v, an angle theta between them, sketch the resultant. Okay, I can put these anywhere. They didn't tell me the x and y components. They didn't give it in reference to the x-axis, so I can put these wherever I want them. So, for example, I can make now, this is when I put the absolute value sign looking thing on there, that means this is the magnitude of u. The magnitude, the length of u is 12. So I would come out here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'm going to draw that vector right there. This is vector u. And then I want to draw vector v. It's 20, but the angle it makes with vector u is 27 degrees. So we make this 27 degrees, and we go out 20 units. 1, 2, 3, 4, and so forth till I get out 20 units. This is V, and this is 20, and this is 12. Let's see if there's anything else they're asking me to do with that. Let's see, for each pair of vectors, u and v, with angle theta between them, sketch the resultant. Okay, I want to add these together. Now, again, two ways I can think of it. One of them is I could draw the line right here, and then I could make a parallelogram out of it, and that would give me the resultant vector right there. So this right here would be the resultant vector. I'd take this vector, it'd make me a parallelogram right here, and make a line parallel right there, and that would do it. One way of doing it. I could also think about it the way we talked about before. I could take this vector, move it here, tail to head, and draw it, and then go tail to head, and this would be the resultant vector. Two different ways that you may describe it, but it actually means the same thing. I did nothing different doing it this way than they're doing it the other way that was shown to us. Okay, let's see what we got next. Let's look on down at problem number 33. It asks us to find the magnitude and the direction of each vector. All right, I'm going to draw the vector. Actually, you work one or two of them, you can do it without drawing it, but I'm going to go ahead and draw this vector. I've got an x value of 15, so I'm going to come out 15 units. And then I've got a y value of -8. I'm going to come down 8 units, and it looks like I have a vector that would be right here. And we would say this is 15, -8. And this represents this vector, starting vector at the origin. The magnitude, that's the length of this. The x component is 15. So from here to here is 15. Y component is -8. From here to here is -8. Now, by the way, if you remember when we're working in our UIL math and we do bearings, I added on the program for bearings the component vectors for the sum of the vectors. And I'm sure you all remember that because we've used that quite a few times in our comp class. But back to this problem. I want to find that distance. That is nothing more than the Pythagorean theorem. So I have the square root of 15 squared plus 8 squared. I'm going to add those together, and I'll let y'all do that. If I take and add those together, I got 15 squared plus 8 squared. I have a note here that that's 17. All right, so the magnitude of this thing is 17. Now then, besides that, it asks us for the direction of the vector. Now, we're in trig, so they're asking us for this angle right here. So to find that angle, multiple ways that we can find that angle. I'm going to use, I can use arc tan, I can use arc sine, matter of fact, I can use arc of any of the functions. Of course, we'd want to use sine, cosine of tan because those are the ones that appear on our graphing calculator. But I could say arc tan of 8/15. Now you say, well, that's negative. Well, yes, I know that's negative, but we're going to take care of that position very shortly. Now let me get my calculator just a minute. Some of my other classes, I hang this up, you know, I do this stuff, but you guys don't probably punch buttons. I know you can punch buttons better than I can. So we're going to go to arc tan. So I go second, tan. I'm going to plug in 8 divided by 15. And when I hit enter, I see that I got 0.418. Now, when I did that, I've got my calculator set in radians right now. I think we're working in degrees. And that being the case, I need to go back and redo this. That was the answer if it were in radians. Of course, I need to go to my mode. And I need to go to degrees, hit enter. And then I'm going to do it again. I got second, tan, and I'm going to plug in 8 divided by 15. Close my parentheses and enter. I see that I get 28.07 something degrees. We're not going to be real ticky about getting it right down to the, you know, the nearest hundredth or thousandth or something like that. I'm going to round that off to 28. So I got 360 minus 28, which would give me what? 332 for an answer. Okay, let me see what else we're going to cover. That was number what? That was 33. So let's go on down to number 37. And on 37, it says for each of the following vectors V has the given direction and magnitude. Find the magnitudes of the horizontal and vertical components. In other words, the X and Y components. When we were covering this stuff in our comp class, we referred to it as X and Y components instead of horizontal and vertical. Of course, we know that horizontal is X and we know that vertical is Y, so it means the same thing. Theta theta the direction of V from the horizontal. Okay, if I look at this thing right here, what we're talking about is this magnitude vector of magnitude 50, and this angle right here is 20 degrees because it says with the horizontal axis. So there we go. And we want to know the X and Y components. The X and Y components are actually the end of that vector right there. we need to know the x value, which we're going to put here, and we need to know the y value, which we're going to put there. X will be equal to, now you can reason through this, or you can go ahead and memorize it. Both of you probably do both. I know that that x is going to be equal to, let me show y. If I were to say cosine of 20 degrees, that would be adjacent, which is x, over hypotenuse, which is 50. Some people just go ahead and say, okay, x is going to be equal to r cosine of the angle, r cosine of 20, which in this case would be 50 cosine of 20. Here's why this works. However, if you do a few of these, all you're going to do is say x is r cosine of theta, and at the same time you're going to say that y is r sine of theta, and that's coming from this definition of sine and cosine. So if I'm looking for my x value in here, I've got 50 cosine of 20. I'm going to use my calculator again to do that. Get my glasses on here a minute. So I've got 50 cosine 20, and when I hit enter, I get 46.98. I'm going to just go ahead and put it down as 47. All right, and for my y value, I'm going to put r, which is 50, and I'm going to put sine of 20, and I'm going to plug that in here. I got 50 sine 20, and when I hit enter, I'm getting 17.1. I'm going to round it off to 17. So here it is in terms of my component vectors. This is equal to approximately 17, actually 17.1 something, and this to approximately 47. Okay, now we'll take a little break, and then after that we're going to come back and we're going to talk about the second part of this, starting at wherever this finished. What did we get to then? We got through 41. All right, so we're going to pick up there shortly when we do B part of the lesson.